We're going to continue on here on this next day on analyzing data in the mole, Unit 2, and we're looking at section 2.3. 2.3, we're going to first define what derived units are in volume and density, and then we're going to compare how they work for regular shaped objects and irregular shaped objects, and ultimately liquids. Definition: derived unit. It's a combination of base units. So we have two terms, volume and density. We'll define those, and then we'll go back to base units and volume, derived units. Volume. So I'm taking this first term, defining its space occupied by an object. Any object will have a volume because it's going to take up a certain amount of space. We have regular objects. Those are the things I can put a ruler on and measure, either a meter stick or a yardstick. And typically we find its volume. We take its length times its width times its height. It's going to give us a resulting number, and then whatever unit we use will be cubed because I have 3 dimensions. I have 1, 2, 3 dimensions. So that little superscript will be cubed. An irregular object, since I can't put a meter on it, like a rock, an irregular shaped rock, it still is an object. It still takes up space. So what I can do then, and you've learned in middle school, is I can use water displacement. I get a graduated cylinder that the rock will fit into, put a certain amount of water into it, put the rock in. Because it's solid, it'll push the water out of the way by an equal volume. So if the water rises up, that difference is the volume of the object. Common units we'll see might be that we're using a meter stick, so it's meters cubed. If we measure the volume of a classroom or your bedroom that you're in, or wherever you're watching the Zoom session, you measure its length in meters, its width in meters, and its height in meters, and you multiply those 3 numbers, and it's meters cubed because you have 3 dimensions, length, width, and height. You might be measuring a textbook or your computer that you're using, in which case you might use centimeters, length, width, height, and it'll be centimeters cubed because again we have 3 dimensions here. Liquids can be either liters or milliliters. When I take that irregular shaped object and I put it in the graduated cylinder, I'm pushing milliliters of water out of the way. But since it's solid, we're going to find out that these two can be used interchangeably. So 1 milliliter equals 1 cubic centimeter by definition. So if I have an ice cube that's 1 cubic centimeter on a side, or it's a cubic centimeter, and I let it melt, what it fills up in a graduated cylinder will be equivalent to 1 milliliter, be that first mark on the graduated cylinder. Density. This is a derived unit. It's the amount of mass, 1 base unit grams, per unit volume. Volume is liters or milliliters. The formula you've seen before is density equals mass divided by volume, where D equals M over V. The unit that goes with density always, since it's mass per volume, is grams over cubic centimeters, or whatever you're measuring in here. It does not change. And I use this little triangle, so if you're algebraically challenged, what you do is that they're going to give you, of these 3 variables, they're going to give you 2, and they're going to ask you for a third. So whatever one they're asking for, cover it up, and it tells you what the formula will be, and then you just plug in those values. So if they want to know volume, you cover it up. So your formula is mass divided by density. If they want to know mass, you cover it up. So your formula is density times volume. These 2 they've given you, so you just plug them in and it'll give you your mass. If they give you density, if they want to find density, you cover it up. Your formula is mass divided by volume. So you just cover up the one that they're asking you for, and the other 2 will give you your equation. There is, in your textbook, if you have the PDF copy or the book itself, it has a list, and we'll go through these more in detail in a later unit, that there are properties of elements, of one of which the property is its density. A density will not change. That's why back in the old days when they used to measure up gold and pay them, they knew that it had a certain volume. You put it in cylinder and have displacement, so they have the volume. And they knew the density of gold, so they could then, since they knew the density and knew the volume, they knew when they put it on the scale, they should get a certain mass. If it was gold, that would be right. If it was lighter, they knew they had something different, or even heavier. They knew it wasn't gold. It might be gold leaf rock, but the mass would not be right. That's because the density never changes. Question is, if something is less dense than water, will it float or sink? And the obvious here we know is that since it can't push water out of the way, it's going to float. So less dense objects will float on top of more dense. You see the color bands here. As they get deeper, these colors, they have different density liquids that are colored differently. In my meteorology class, we studied this when we studied the oceans. We actually do this experiment. The density of water, by definition, is 1 gram per milliliter. So if I have a mill of water, and I put that on a scale all by itself, it'll weigh 1 gram. They knew that, and so everybody, the scientists, decided that was going to be their standard. And that's how they do graduated cylinders. As they put more and more grams of water in, they can mark it off. You got 10 grams, they put a mark, that's a 10 milliliter mark, and so on. Let's try a little practice with this. You have a piece of aluminum, its density is 2.7 grams per cubic centimeter. So we see the grams per cubic centimeter, we know we're looking at density. And it'll not change for all aluminum will weigh that has this density. Excuse me. You place it in a graduated cylinder that has about 10.5 mils of water. The water will all of a sudden rise up to 13.5 because you put this in here. What's the mass of the aluminum? This is the displacement mass. My mass, I have to tease it out a little bit because it's an irregular shaped piece of aluminum. I have to get its volume by taking the difference between those two. So the unknown here is the mass. They're asking, what's the mass? So we're going to cover that up. That leaves the equation D times V, or density times volume. There's the density. The volume will be the difference here. So I cover up the mass. There's my equation. Since it's irregular shape, it requires the displacement method to measure the volume. So that'd be 13.5 minus 10.5 will give us 3 mils for volume. So when you put it in there, it goes from 10, pushed out of the way. That difference is the equivalent volume of the object, or 3.5 mils. 13.5 minus 10.5 gives you, whoops, typo, 3.0 it should be, not 3.5. So I have a typo here. Sorry about that. It should be 3.0 mils. I'll have to correct that. So the density they've given to you bottom, you solve it. You're going to take this times 3.0 mils, and that will give you your volume. Or mass, I'm sorry, 8.1 grams. So you're not going to get this if you use this number. You've got to use 3.0. Which of the following is a derived unit? Yard, second, meter, kilogram, miles per hour. If you guessed number 5, you were right. And how do I know? I've got 2 unit labels here. They don't cancel out. That tells you it's derived. I've got 2 base units. Miles is distance, hour is time. What is the relationship between mass and volume called? You said density? Good job, because that's what we covered today. And that's the end of this unit section, and we'll have some problems for you to do as well.